So, what I want to discuss is about proper maps. Proper maps and complete variety. So, these proper maps are, I mean, you know, in topological space. So, complete variety. So, these are analog of compact spaces in topologicals. But see, in the category, this is analog of compactness in algebraic geometry. But the usual compactness definition, it does not work because the open sets are huge, the risky open subset. Everything is compact. So, one should have some good theory of like. So, they are called complete varieties, and we will see later that all projective varieties are complete. So, like so they are good. Do you think that projective varieties, these are compact in the sense of algebraic geometry? Affines are not. Affines are not complete. And proper maps, these are also analog of the proper maps in the usual topological space. So, I will come to that. So, this is some. So, you can do it at the morphism level. That's then this comes. Okay, so let's look at the first. Let's state the definition. X is complete. X is any variety or P variety. Assume X is a variety. X is complete if the second projection map P2 from X cross Y. This is product in the category of varieties to Y is closed for all Y. Okay, or this is equivalent of saying that this is universally closed. You take this X cross point, everything collapses to a point, then this is universally closed. So, what is universally closed means that when you do the base change, then if you do a base change to this morphism, then it becomes X cross Y, right? Over a point, the fiber product, this is the projection map. So, this is universally closed. This is another way of saying that this is
universally closed means X2, that point map is
universally closed if this happens for all Y.
But diagram coming.
Yeah. No, this map is closed. P2 is closed.
P2 is closed.
So, this statement is is that P2 X, it is true for every Y, is same as saying that this is universally closed, right? That is what it means. And you say that you try to generalize this for the morphism, then you say that a map X to Y is proper if it is universally closed. So, what does it mean? That means that for every Z in Y, X cross Z fiber product over Y, this map P2 is closed for all Z. Okay, in particular, if you just take Y is a point, right? Then x2 point is proper in saying that it is it is complete. X is complete. So x2 point, x is complete implies that x2 point this map is proper. So you try to generalize this completeness in this language. Okay. So now, so first of all, there are plenty of examples where this is not closed. For example, you in the case of affine, you know that you take this set xy equal to 1 variety. So this is A2. So A2 I can think as A1 cross A1, right? The product. So this is now you have this map, right? So it goes to, you project it to the second coordinate or first coordinate. So this, so then this is the image is A1 minus 0, right? So image is, so this goes to A1 minus 0, which is not closed. This is a closed subset. The image is not closed. So that will say that A1 is not complete, because this is a fiber product A1 cross, you take the point A1 to point and A1 to point. So this will imply that A1 is not complete. In the same way, you can show that the affines are not complete. So the main theorem of this section is that Pn is a complete variety. That's that's the main result of for proper maps. I mean that's the kind of, that is the theorem to prove. But before that, some consequences. This proper maps has some. So you understand that proper maps are very general object. Right? If you study proper maps, then you study complete varieties in general, right? So properties of proper maps. So proposition, composition of proper is proper. So there are always two things. Whenever you have some morphism, you can talk about either composition and the base change. So this is base change of proper is proper. So this says that if you have a map from x to y, so z such that x cross z y, and if you call this f is proper, implies g is proper. Closed immersions are proper. If x is complete, then any morphism x to y is proper. Ah. 5. If y is open cover, say Vi, affine open cover, such that F inverse Vi's are, so the F inverse Vi to Vi is proper, implies F is proper. So in some sense it is a local property. If you have an open subset and inverse image to Vi, then F is proper. Okay. So now some sketch of the proof.
What about finite maps?
Finite maps are proper. That
Definition or
no, you require that projectives are complete. The PN is complete that you need. Finite maps are proper. It is almost by day. Yeah, I can include that finite maps are proper. You don't need projectivity because if it is finite, let's see why this composition of proper. First of all, composition of proper is proper. Okay. So what you do? So this is the thing in the fiber product. See x to y and y to z. Okay, and then suppose you have a map from W to Z. So let's call this F. This is G. Then you have this fiber product W cross Y over Z. You have this, and you have this W cross Y O X. Now the point is that this diagram commutes, will say that this rectangle also, this diagram also commutes. And the point is that W cross Y is same as W cross X under this map G composition F. Because X to Z there is a map, right? G composition F. Then W cross X Z. So this is basically when you do this base change, affine at the affine level, it is just tensor product, right? This is something like you have done this exercise in your R tensor S tensor T S, right, over some say A. This is same as R tensor T, something like this. If S and T are A algebra and R is a S algebra, then you can take S this side, then it becomes R tensor T over. So this is basically that is what happening here at the affine level, right? So this is isomorphism. So now you know that this guy G Y to Z is proper. So that will say if I call this G prime, so G prime is closed because under base change, right? This map is closed map. Definition, what is a proper map? Under base change, it is a closed map, universally closed. So now this is now F prime. Similarly, F is any arbitrary map from X to Y. F is a proper map. So that will say that this F prime is closed. So that will say G prime composition of closed map is closed. So so these are given proper. So that will say that this is proper, right? So composition of closed is closed, and you use this identity. So that will say that this is proper. This is closed. So that will say this X to the composition of proper is proper, right? Now, the second one is what? Yeah. So, this is also similar, because if you have something, so what it says, under base change it is proper, right? So, suppose y, okay, let us write x to y, x to y. Okay. Now, you get a something, a w cross x f prime. Now, if you further change, so what you want to do, f is proper, you know, you want to prove the f prime is proper. So, again you say some, say w prime. So, then it will be w prime cross w, or w prime cross w cross x over y, right? This is over x. So, now this you want to, but you want to prove this is closed, but this map is the fiber product of this map and along with the composition, right? Because f is proper, we will say that this is closed, but that means that this is proper, right? Because you want to prove that this map is closed, f is proper, we will say give you a map f prime. So, that will say that, so f is proper, we will say that this map is proper. So, that says that f prime is, this is arbitrary map. So, we will say that f prime is, so under base change it is proper, under base change f proper is proper. Okay. So, proper maps are proper, remains proper under base change. So, composition, now if x is complete and if you have a morphism from x to y, it is proper. So, I will come to this when I do the complete projective variety. One second. Oh, okay. Third one is that closed immersions are proper. So, how do you prove? So, x to y is a closed immersion. This is a proper, right? So, closed immersions also remain, it is invariant under base change, right? If something is a closed immersion and if you have a map from z to y, then x cross z to z, this is also closed immersion, right? You see, at the ring level it is true. So, closed immersion means it is surjective. So, it is true. So, that will say that closed immersions are the, it is they are proper. This is closed. And the fourth one is what? X is complete. So, x is complete. So, you embed x into some y, x to y there is a map and you take this projection map P2. So, this x to x cross y is a closed immersion. So, first of all, the 2 will imply the projections are proper. I mean, this is projection maps are proper. If you take any projection map x cross y to y, this takes closed subset to closed subset. This is an example of a proper map. This is I'm saying. So now this is projection maps are proper. I is a inclusion. This is a closed immersion. X to x cross y. You take x to some fix a point in y. Send it to x cross y. This is a closed immersion, and composition of proper is proper. So that will say that x to, if I take, sorry, what I am writing, not x cross y, x cross x comma fx. Given a map x to y, I embed x into x cross y. You take the graph. This is a closed immersion. We are in variety level, right? X and y are varieties. So this is a closed immersion. So, and this is a projection map is proper. So composition of proper is proper. So that will say that x to y. Any map from complete variety to sorry, projection maps are proper. Here I have to be little careful. Not for any of course, if x and y, if you take a1 and y is a1, that a2 to a1, this map is not proper map, right? Because you take the closed subset xy equal to 1, that is not going to a closed subset. So you have to be careful that when projection maps are proper, when x is complete. Second projection, x is complete. Because this follows, because x is complete means x to point, this is universally closed. So that means that x cross y to y, this map is closed. So that will say that this map is, again you do another, this is closed. Now closed map will under base change, again it will be a closed map. So that will say that this is a proper map. So when, because x is complete. So if x is complete, then the projection maps are proper. So that will say the any map from a complete variety to any y, this map is proper. So in something you consider any map f from a projective variety, so we will see that projective varieties are complete. So projective variety to any y, this map is a proper map. And projective variety to affine variety, there are no maps. So only because there are no regular functions, so only y can be projective. So map of projective varieties, these are proper maps. So now you understand that why proper maps are so important. I mean, any map between projective varieties are proper, because projective varieties are complete. Projective spaces are complete, and any projective variety is a closed immersion in some projective variety, projective space. Closed immersions are proper, right? So that will say that projective varieties are complete, right? What I am saying that you know that Pn is complete. So Pn to point, right? Now this is a closed immersion. So this will say that x is complete. So any map between projective varieties, they are proper maps. So study of proper maps is very important then, because after all this is a okay. Okay, so what I am saying that now the theorem, the theorem of this.
Finite maps are proper, I think that's not true. Finite morphisms are proper. Like if we take the projection from like a2 minus 0 to a1, I think that is finite but not proper.
Why it is finite? If it is finite at the ring level, it will be a finite ring.
Because it's like it's a map. The induced map is from kxy to kxy.
No, kx.
Yeah, sorry, kx to kxy.
That's not a finite map.
Y square module level is
Pn is complete. So this is the theorem. Many consequences will come from this. I will give a proof, maybe not today, I do not have time much. It requires some calculations. I will come into the next class, I will give a proof. But let us see the consequences. So, the one which I was saying, that if x is projective, then x is complete. So, that means closed subset of complete projective spaces, they are complete. And also any morphism, that is just because we saw right now that if x is a complete variety, then x to any morphism is proper. So, any morphism x to y is proper. Right? No, 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 y is nothing, y is anything. X is just projective. So, why x is projective implies x is complete. So, that is because x you can embed it into Pn, this is inclusion, and Pn to point, this is a so Pn is complete. This implies Pn to point, this map is proper. Right? What do you mean by proper? Proper means that Pn cross Z to Z, that map is closed. Now, what do you mean by complete? Pn is complete means this Pn cross Z to Z, that second projection, that is proper. That is exactly the definition of completeness. Right. So, this is a Pn is from Pn, this map is proper. Now inclusion, now you know that x is the inclusion, the closed immersion, x to a Pn is a closed immersion, this is proper. So, this will imply that x to point, the composition is proper. But x to point is proper is same as saying that x is complete, right? Because it says that x cross Z to Z is x to point is universally closed. So, that is same as saying that this is proper. This implies x is complete. Right. Okay. So, now let us come to this finite morphisms. The point is that the fact that finite morphisms are proper, and any proper morphism with finite fiber are finite. See, finite maps with finite fibers, they are called quasi-finite, they need not be finite always. But if it is a proper map with a finite fiber, then it is a finite map. Finite map is more than just finite fiber, because there is some integrality condition, and you can find some examples, and maybe in next class I will talk about some examples where finite fibers does not imply map is finite. There are plenty of examples. But if it is a proper map with finite fiber, then the map is finite. Right? So, finite morphism. So, recall that what is a finite map? X to y is finite. If you have open cover, x union of ui such that f inverse of ui is affine, and f inverse of ui to ui, you have this map is finite map. So, what do you mean by that? That means that O of ui to O of y ui to O x of f inverse of ui, this is a integral, this is integral over this, or this is integral or finitely generated O y ui module, right? Finite is integral or finite module over this, right? So, now we know that finite also, you have seen that finite maps under base change it remains finite, right? Because integrality condition, it is remain invariant under base change. Composition of finite is also finite. So, you expect that it is proper. Proper map also has that property. That under base change and composition it has. Yeah, this is a very local property. Properness is also a local property. So, that is why it works. You can make this definition globally. You do it for affine level and then you say that locally is a. Though for proper map you do not require the inverse image of affine is affine. The way you have defined properness, you did not use, here you are using the inverse. So, finite maps are affine maps, that means inverse image of affine is affine. But in the definition of proper, it is more general. You do not expect the inverse image of affine is affine. But as a special, but this is a special case, the finite maps. So, proper maps in the they are very general morphism, right. First of all, the finite morphism has finite fiber. Is that clear? Because if something is integral over, if it is a finitely generated model, these are Artinian rings. I mean, so that will, I mean, so because if you, I mean, Artinian rings, that means if you take a x to y, if this is a finite map, if you restrict to a point or maximal ideal, so this is a k vector space, this is spec k, it is a point. So, what is the corresponding ring? It is a vector, it is a field. And then the inverse image will be a, so this is also affine by, so inverse image will be some vector space, which is a Artinian ring, which is a ring which is a vector, finite dimensional vector space, and it is a Artinian ring. In Artinian ring, you have finitely many prime ideals. So, that will say that, so there are finitely many maximal ideals. So, finite maps always have finite fibers, right. So, finite, as a consequence, that finite maps always have, implies finite fibers, but not opposite. But the converse is not true. Find examples. Okay. Fine. So, now what I am saying, this finite, because it has good properties under base change, and when you see finite maps are also closed maps, and under base change it remains closed.
So, why Artinian ring has only finitely many prime ideals?
That is a result. If it is an Artinian ring, it has finitely many prime ideals. In particular, it has it's a result in commutative algebra.
And these prime ideals correspond to that finite fiber.
Yeah. That's how. Maximal ideals, not prime ideals. Anyway, so now the point is that finite maps, they are closed maps. They under base change also it is closed. That's exactly the local definition of properness. right? It is proper if the F inverse ui to ui, this map is under it is proper. That means that when you it is universally closed, and that's for finite maps that holds. So that will say that finite maps are. Is it clear now? That why finite maps are proper. So this will say that finite maps are proper maps. A finite, I should not say more maps, morphism.
In this case, finite map and finite morphism. Finite map and finite morphism.
Yeah. Finite. But converse, the converse is also true, that proper, if it is a what I was saying, that proper morphism with finite fiber are finite morphisms.
Finite fiber means finite.
Yes, I mean quasi-finite. The finite fiber, these are called in algebraic geometry quasi-finite map. Like quasi-compact. Quasi-compact is basically compact. Finite cover. But it's not a good definition for algebraic geometry. That's why it's called quasi. You need some more condition to have a good properties of the algebra, so that then you say that it's a compact, like proper and quasi-finite. It's fine. It's fine marks. Okay. So I will stop here. So only thing we have to see that this theorem Pn is complete. So this is the theorem of this, and maybe in next class I will do it. I will stop here.